My name is Dave Sparks, and I'm the technical lead on the Android Media Framework. And I'm going to give a talk this afternoon about advanced audio techniques in Android, and also give you some highlights about the Froyo release that we just announced today, and then talk a little bit about roadmap. So if you're going to follow along in Wave, here's the URL. And I'll leave this slide up for a little bit so you have a chance to type it in if you want to follow along there. So a few questions. How many people here are active Android developers? So you've written an application. OK. How many people actually have an application up in market? Wow, that's a pretty good showing. Not bad. And anybody have more than one? All right. A few hardcore developers. So everybody get a chance to see the Android keynote this morning? Not many people? OK, well, one of the exciting things we announced this morning was the Google TV stuff. It's pretty exciting, I think. So did everybody hear about Google TV? Yes. Yeah. So anybody interested in developing for Google TV as well? Yes. All right. OK. So anyway, I'm just trying to get a feeling for where people are in terms of development and excitement about Android. So we'll move on. Hopefully you had a chance to get that URL. So the agenda today, I'm going to talk about native audio signal processing in Android. There's been a lot of interest in doing something more than manipulating bytes in Java code. So I'll give you some sample code snippets that you can use to get started. We'll talk a little bit about resource and power management. I revisit this every time I do talks or anytime I talk to developers about it. Battery power usage and resource management is really critical on these battery-powered devices, obviously. So we'll talk a little bit about that. As I mentioned earlier, I'm going to talk about some of the new stuff we've thrown into Froyo. We think some of it's pretty exciting. And then finally, we'll talk a bit about the roadmap for future releases and some of the stuff we're working on right now. And then hopefully we'll have at least a few minutes at the end for Q&A. We're going to try to catch up a little bit. I guess the keynote ran long this morning, and we're kind of behind on the schedule. So I'll try to go fast and not lose too many people. So we'll start with talking about native audio signal processing on Android. So everything we do in Android right now, basically you're doing through some sort of Java interface. So I'll start with an overview of the audio track interface in Android, just so you have a sense of how you connect into things. So we'll look at Java code first. So the audio track interface is basically a raw PCM audio interface. You give it raw 16-bit or 8-bit audio, and it gets mixed in through an audio subsystem we call Audio Flinger. Does whatever sample rate conversion it needs to do to get to the sample output of the device. And then you can do mixing, left-right balance, things like that in the API. So it basically gives you a way to send your application's audio directly to an output. So you can generate that. You could take a WAV file and output it, whatever you want to do with the audio. We have people doing things like soundboards and synthesizers and stuff like that using this interface. It allows you to do both streaming and static buffers. So a streaming buffer meaning you're generating the audio on the fly. Maybe you're streaming it over a network connection, or you're reading out of a file, but you have a small buffer. You fill the buffer, and there's a read pointer and a write pointer, and the write pointer needs to stay ahead of the read pointer, and you just loop back. So that's the streaming mode. There's also a static mode where you can fill it up with typically a small sound that you're going to play a lot. An example might be a prompt, a beep or something, or a gunshot in a game. So it allows you, it's actually very low overhead because that data gets buffered up in the Audio Flinger service, and you don't actually have data flowing across from the application side to the server side. You can set callbacks to refill the buffer. So in the case where you're doing streaming, you can set a callback, say, halfway through the buffer. That prompts you to go generate buffer, new audio for the part of the buffer that just emptied. So it uses a pull model that way. You can also retrieve the play position. So if you're trying to do some long stream, if you want to do synchronization in a game or something like that, you can find out where the play pointer is at any particular time. And it takes into account the latency in the audio path. Now, obviously, this is really useful for games, if you're doing streaming audio, any kind of thing where you're generating audio on the fly. So here's some sample code using the Java interface, and then we'll dive a little deeper into this and see how we do it with native code. So if you look at up here, we're basically, we've got this class called audio track sample, and it implements runnable, so it's going to spin off a thread that's generating audio. And we've declared a few variables here. In buffer size is the size of the buffer in samples. In this case, it's 8,000, which translates to about roughly 180 milliseconds of audio, but you choose whatever you want. There are some constraints on that. We need to buffer enough audio that we're not running out of data and having audio break up. So you may need to experiment with that, depending on your application. Mtrack is the audio track object itself. And then mbuffer is the audio sampler buffer. And then msample is a state variable we'll talk about later, which we use for generating audio. So in this next slide, you'll see where that comes into play. So we start out by initializing the buffer, and we create an audio track. In this case, it's a music stream. So in Android, we have this concept of different streams types, and each of those stream types has their own individual volume control. So if you're doing a game or something that's typically a foreground application, you probably want to use the music stream. Ringtones and notifications are controlled by a different stream. So we have, basically you can set different audio levels for different types of streams. And in this case, it's a mono output, so we're just generating one channel. The audio mixer will automatically reflect that to both left and right channels if it's a stereo output. And then the buffer size is specified in bytes, so that's why we're multiplying the buffer size by 2 when you look at that. In buffer size times 2, it's because audio track wants the buffer size in bytes. And we want the track to operate in stream mode because we're going to be generating this audio on the fly. And then the run function here, next part of the slide here, we start playing the track. That basically arms the track to start playing. And then as soon as you've buffered enough audio, it'll actually start outputting to the audio output device. And then we just have a loop, while one loop to generate the audio and write it to the audio track. So those are the next 2 lines there. Obviously, if you were doing a real application, you'd need something a little more than that because you probably want to stop at some point. So I haven't implemented that code. It wouldn't all fit on the slide, but I think you get the idea. So moving on, this is the code that actually is going to generate a tone. And I use something really simple here. We're just generating a sawtooth wave. It's basically just a linear ramp. It sounds like a fat synthesizer sound. So at this rate, by adding 600, we're going to wrap around, and we generate roughly a 400 hertz sawtooth. So it's just filling the buffer with some really simple audio. So that's basically how the Java interface works. Now, if you want to use native code, first thing is you need to download the Android NDK. So you've got the Android SDK. You're going to download the NDK as well. You're going to build a Java application. You start with a Java app, and you're going to add the native code to it as a library. So once you have your Java app built, like let's say this one, you create a native library, and that really just involves writing some source code. You can take a sample makefile from the NDK and use that to build your library. And the library will have basically implementations of Java methods that are declared in the Java object. And so that's basically, we add a native method to a Java class, and we can call the native code from Java. And then in the Java class itself, at some point, you need to load the native library to allow the VM to link the methods that you've declared in the Java class to the actual native code. And then you just call your native methods from Java just like you would anything else. So we'll take a look at some actual native code here. So this is going back to our Java sample. This is the Java code again. This is actually the same as the first slide. Nothing has changed here. We're doing all the same things. All the magic happens on the next page, which is where we were doing the generate tone stuff before. So now if you look at it, we have this static declaration here, system load library, and that actually loads a .so file called generate_tone.so. So that's where the native code is getting written. So when you're doing your native code in this particular example, I'd probably have a generate tone.c or C++ file. And in that file, I would have my native code. I'd build it, link it, and I end up with an SO. And this is how it gets loaded. So as soon as this class gets loaded in your application, the VM is going to go look for that library, load it, and it will do the links from the Java code to the native code for you. And that all happens automatically. And then in this next section, we have the public native int generate tone. So basically, this is the same call signature we had for the Java object. We just added a native thing to it, and that tells the Java bytecode generator to look for an external symbol, which is this native code. And then here we're moving on to the actual native code. So this is in C++, and you're going to have a function here, generate tone, and it needs to have the package signature and class signature that you declared in your Java class. So going back to the Java class, it was com.example.jnisample.jnisample is the class, and generate tone is the method. So this is how the linker finds the method and links it up. Now this works if you have a single call signature. So in other words, if I only have one generate tone and it will be able to find it that way. If you have multiple, if you've got an overloaded method, then you're going to need to do something more sophisticated than that, which gives it the actual call signature with the parameters. But for a simple sort of thing like this is the easiest way to do it. You just have one method and no overloading. It's really simple to get this to work. So just some simple stuff. You typically, when you're writing native code, you want to do some sanity checking on the parameters you're getting from Java. So, because it's easy to end up with a crash in native code as opposed to in Java where you get a stack trace. If it happens in native code, you're not going to get the nice stack trace. And if you remember this morning, if you were at the keynote, we have this new reporting code in Market that allows you to get stack traces if you have a Java crash, where you're not going to get those nice traces if it happens in native code. So make sure your native code is clean. So here we're just checking to make sure that we're getting a reasonable value for size. And then the next line we call get primitive array critical, and we're passing in the buffer pointer, or basically the buffer Java buffer object. And we get back a C short star pointer. So that's the actual pointer to the buffer data that Java would see. So it basically gives us the hooks we need to go access that buffer from C code. One critical thing here, basically this is pinning that array in memory so that it can't be GC'd. So during a GC, it could potentially move around. So this is basically telling the VM, don't move that code I'm doing, or that object, I'm doing something with it. And of course, at the end of that, you need to make sure you release it. So now that we've got a valid pointer to the buffer, and we're going to check that, obviously, to make sure that we actually get a valid pointer back, because it's possible that object might have been, might not be a valid Java object. So doing another check there to make sure pdata is actually not null. Then we basically have implemented that code to fill the buffer with audio in C here. So it's pretty much the same algorithm. We start with a sample of 0, fill it up, wrap the have the value advance by 600 each time. And that gives us, again, roughly a 400 hertz tone. And at the end there, the release primitive critical array, basically that array critical, unpins that memory and allows a GC to happen if necessary later on. So it's really simple way to take advantage of native C processing. So this is a way if you wanted to do something sophisticated like maybe a synthesizer engine or your own mixer, audio mixer, or do some signal processing in C, you could hook into the existing audio track class to do that. So there's one little difference in this code from what we had in the Java code. In the Java code, that sawtooth generator, we were actually saving the state of the sawtooth generator at the end of each generate tone in a variable called msample. In the C code I just showed you, I wasn't doing that, and we'd actually end up with discontinuity in the signal. So the reason I didn't include that is it wouldn't, if I'd put that on one slide, you wouldn't be able to read it. So I've broken it up into a couple of pieces. Now we're going to see how from C code you can access other Java objects. So going back to the same code, I've kind of pulled out some stuff, the code to pin the data array and stuff like that, and I'm focusing now on that one little section of code that actually generates the tone. So at the beginning of this function, we see, well, if you look at the top, you see a static value there, which is msample field. This is an index that basically gives us a way to get at the Java objects from the Java members from the Java object itself. So at the beginning of this function, we check to see if that's 0. Since it was static and initialized to 0, the first time you call this function, it's going to be 0. And then what we do is we look up the class through the Java environment. So in the call of the signature of this function, we get the Java VM environment, and we also get the object. So we're going to use the Java VM to call find class, and we know the name of that package. So we're going to go look for that class, and we get back a field ID for the class itself. And assuming we actually find that class, and it's hard to believe that might fail, but here's the sanity check just in case. We then do a lookup with get field ID for the member called msample. So in Java, we called this is an int member of the Java class. So we're looking that up, and the S tells it that it's a short type. So we know there's a variable, we're looking for a variable msample type short that's in the class com.example.jni sample.jni sample. And it should return back a value that's not 0. And that's the handle you need to get at the object within the member of that class, that particular object. So I've commented out the code there that actually does the pinning the data buffer. And instead, we're going to focus on the actual tone generator. So the first thing we do is we call get short field. And we're passing in this, which is the pointer to the Java object we got in the call to this native function. And we're passing msample field, which is the index in the class, to that member within the Java object. And we get back the value of that object. So now we've able to retrieve state from the Java side. And then in the function, we use that to generate the tone. So now we can start with the last sample, and we continue generating from where we were. This little loop is the same as it was before. Then at the end, we're going to save that value back into the Java object itself. So set short field, we pass in the Java object pointer, msample field, which is the field we want to set, and the actual value that we want to set it to. And then what that'll do is now reflect that value up into Java. So this allows you to store state information in native code in the Java object itself instead of having to keep a separate set of a structure or something like that to store that code. If you're just doing a few variables, this is probably the way you want to do it. The other option you can do is you can store a pointer. There's some, since Java doesn't have a native pointer type, there's some pitfalls to that. At some point, if we change to larger 64-bit pointers, for example, if we ever had a device that had that, you could run into problems. But we do a lot of this stuff in the platform code where we will store a pointer to a bunch of data, because there is a fairly good cost to looking up the value of the Java object through the VM. So if you have a lot of state information, you might want to consider saving that as a C structure or something. So you allocate it when the object is created, and you deallocate it when it's released. It's a little trickier to get that right because you have to do all the correct record keeping to make sure you're not leaking memory. So that's kind of the quick take through of the native signal processing. I'm going to just really quickly run through the power and resource stuff. If you've seen me before, I say this every time. Make sure you call release on media objects. Almost every object that we have in the media framework has a release call. The reason for the release call is if you don't call release, you have to wait for a GC to actually call the finalizer, and that's when the resources are deallocated. Typically, for example, let's say you've got a media player. There's very likely a hardware codec that's been instantiated in the media server to decode video or decode audio. And as long as you're holding that media object, that media player object in your Java class or Java application, there are resources in the media server that are being consumed. That includes potentially battery power, DSP, et cetera, et cetera. So you want to make sure you clean those up quickly. And if you wait for a GC, it may be 5-10 seconds, who knows, before the GC happens. Just depends on how much memory pressure that is. So the release basically forces it to immediately do a finalize on any of the native resources that have been allocated. So that's really critical for battery power and also for interoperability. You don't want to be holding onto an object that potentially another application might want to use, or even another activity in your own application. And as I say, it powers down unneeded hardware. In many cases, for example, if we have a hardware codec, we're powering up a DSP that's consuming maybe 40 or 50 milliamps more than the device consumes without the DSP turned on. And that can have a significant impact on battery life over the long run. And like I say, it's nice to cooperate with other applications. If you're getting switched out, another application is coming up and it needs that same resource, it may not be able to get it. So making sure you call release during the on pause, make sure that other applications can get access to it. And another critical thing is making sure that you're actually calling from on pause and not from on destroy. There are circumstances where you may not immediately get a call to your on destroy in your activity. And in that case, a good example is from the home screen. If you have an application running and somebody hits the home button, you typically don't immediately get an on destroy. And so you need to take that into consideration. You really should do it in the on pause. So kind of moving quickly on to the next segment, we're going to talk about what's new in Froyo. We have a new API we call audio focus, basically audio focus and transport control API. I will get into this a little bit later with some sample code. We've made some improvements to Soundpool, some things that people have requested. We've also added some improvements and a way to route audio specifically in an application. This is to accommodate things like voicemail. And I'll go over that a little bit later. And then we also made some improvements to the camera. So here we go. So audio focus and transport APIs. If you've done any development on Android or have done anything particularly with audio, there's been a lot of problems with conflicts between applications, particularly if you have an application that's playing in the background and streaming audio or music playing or podcasts or whatever. There were some things we did early on that were probably not the best decisions. And so we went back and we looked at that and we said, how can we improve the situation with cooperating between applications that want to play audio? This particularly became a little distressing when we launched the navigation, turn-by-turn navigation, because here's an application that wants to periodically inject voice prompts so you can, find out where you're going. You're in the car. But if you're listening to a podcast, having the voice prompts over the top of a podcast is really, really distracting. So we wanted to make sure we could handle that use case. There are a number of other use cases. And I have a quick little demo that we'll do in a minute that just shows how that works. So one of the things in designing this new API is we wanted to make sure that we left developers in control of their own applications. Now, there are a couple of ways we could have gone about this. One is we could enforce it at the system level and dictate, only one app is ever going to make audio, be able to generate audio, and that's it. And that's not what Android is about. So we actually made a choice to say, how can we give applications the information they need to make good choices about audio and do innovation? So that's basically one of the philosophies when we were designing this. So basically, the way it works is apps and services can register to receive events about what's happening with audio focus. They can request audio focus. So the concept of audio focus is my application needs to be in the foreground of audio. It's going to be producing something that the user needs to pay attention to. An example of that might be the ringtone. It might be a music player app. It might be YouTube. It might be streaming audio. It might be an email notification. But for some reason, you want to draw the user's attention, and that should be the focal point as far as audio is concerned. It doesn't necessarily get associated with the app that's in the foreground. If I'm browsing the web, it's perfectly fine for audio to be streaming in the background. But if there's a web app that wants to make a sound, then we need a way to enable that to take control. Another kind of unique thing is that the audio focus request can be either a permanent request, in other words, I want to take over, or it can be a transient request. A transient request, good example of a transient request is like an email notification. We're just going to briefly interrupt the audio, and then we're going to come back. So the app will know, the background app, the app that's losing focus will know, hey, you're temporarily losing it, you're going to get it back later. And we've also included something called a ducking hint. If you're familiar with, it kind of goes back to the old radio days when the DJs would talk over the audio. Ducking is reducing the volume so that you can talk over the top of it. And so for applications that are requesting focus, they can give a hint to other applications, hey, it's okay if you go ahead and continue playing, just reduce your volume. And the idea there, if you think about the navigation thing, if music is playing, it's perfectly fine for that to continue playing, just make it a little bit softer so I can hear the navigation prompt. And then when the application is done, it should abandon focus. So basically, I'm done doing my thing, send it back to, send the focus back to the previous app. And then the transport controls work in the same way. So transport controls, if you've got the wired headset or if you've got a Bluetooth headset that has next track, previous track type controls, pause, resume, those controls, we had the same sort of issues with apps competing over that. So the transport controls now follow this sort of same paradigm of an application can request them and take over control of it. So I don't have two apps that are competing. We had situations where somebody would hit the play button and two applications would try to start playing at the same time. So this resolves that issue. And then what we've done is we have helper classes that will be available that using reflection will enable you to put this in your application and still be backwards compatible. So you can write an app that's compatible with Donut and take advantage of these new APIs that are in Froyo. So I'm going to show you a little bit of code here. Not too much. It's pretty simple. So in your, this particular sample is really aimed at a service. So this would be music application or a podcast or something that's playing in background. If you're doing an app that's playing in foreground, you'd probably put your hooks in different places. You'd put it in on resume and on pause instead. But in this case, we're going to do it in on create and on destroy because it's a service. So in on create, we get a reference to the audio manager. We're also going to tell it, in this particular case, that the streams we're outputting are stream music type. This basically tells the system how the volume control should behave when that app is in the foreground. So the volume controls will get routed to the music stream instead of a ringtone or something else. The next thing is, so I've kind of have an abstract concept. So when the application starts playing, you set this flag, playing is true, and you start your thing. And then at the very top of it, you can see requesting audio focus. So that tells the system this application is now moving to the foreground in audio. And then when the stream stops playing, you are going to set the playing flag to false. And if we're not going to restart afterwards, we're going to change the, basically abandon audio focus. So we're going to lose focus. So this is a case where the user has deliberately said, I'm done with this application, I'm going to stop playing. We'll see how the restart flag works in the next page of code. And then on destroy, we always abandon focus. So this takes your application out of the audio focus stack. So in the next slide, this is kind of where the root of things happen with the system. So there's this new interface called on audio focus change listener. So we're creating a new on audio focus listener, on audio focus change listener. That's a long thing to say. And it has a public method on audio focus change. So you'll get a call anytime audio focus changes to your application. It's either going away or it's coming back to you. So you can see here, we're going to switch on what event took place. And in the top, the first part here, it says audio focus loss. So we're losing audio focus. So at that point, we're losing audio focus, and then we're losing it permanently. In other words, some other application has said, I'm taking over audio now. And so in this case, we set our restart flag to false. Restart flag tells us whether we're going to restart later on. Since we're losing it permanently, there's no point in restarting. The only way that's going to happen is if the user actually goes back and says, I want to start this application again. In the case where it's a transient loss, we're going to treat both transient and transient can duck the same. And I'll show you how you can do the can duck a little bit later. So we set our restart flag to true. That means we've lost focus temporarily. We're going to get it back. And when we get it back, we want to start playing again. And then we just pause the audio stream. And then in this last case here, when we get the focus back, if we're not playing and the restart flag is set, we're going to go ahead and resume playing and set the restart to false. So now we've got audio focus back. And this is how you resume back when whatever else was going on has finished. You get focus back and you start playing again. So an example of this would be, let's say an email notification comes in and it wants to play the little, whatever you've chosen for your notification tone. You're first going to get audio focus transient, and that will tell you you've lost focus temporarily. Then you'll get audio focus gain, and that's when you restart your app. So audio focus transient, stop playing, audio focus gain, start playing. So it's pretty easy to implement this. The nice thing about this is that once you've implemented this, the old tricks you might have used earlier to look at the call state, like the music app used to do this, where it would look and say, if the phone is ringing, then I'm going to resume afterwards. You don't have to worry about that anymore. This API will handle all of that. So it's just one simple set of code you have to worry about. And then this next bit of code shows how you might handle ducking. So in a case where for a podcast type of application, you probably don't want to duck. It doesn't make sense to have, the audio talking, from a podcast go over some other prompt. But if it's a music application, streaming music or some music player, it's probably okay to have that continue playing in the background. So in this case, all the code for transient loss is the same as before, but for the can duck case, we have a slightly different set of code here. So in this case, I'm setting a flag mDucking that says I'm ducking my volume temporarily to true. I save the old volume, and I set my volume to the new volume. And the new volume in this case is whatever that is, an eighth. It's like down 18 dB. And so now I've reduced the volume of my output track while whatever it is playing continues to play. And when I get focused back, if I was ducking, the first part of this clause is the same as before. The second part of the clause is if I ducked, then I'm just going to restore the old volume. So this is why you can, in your application, do something slightly different, maybe a better experience for the user. Your choice, though. Then we have Soundpool improvements. Sorry, that was kind of quick transition there. We'll have sample code for this, by the way, when we release the SDK, or on probably a blog entry coming up soon, and it'll include the reflection code, probably some sample code on how a service might work. So going back to Soundpool, a couple of things we got asked about in Soundpool. One of the problems people run into is the loading of sounds is asynchronous, and they wanted a way to know when a sound was loaded. And so we added a new callback for once a sound is loaded, you get a callback. It tells you what sound got loaded. So now you have a way of knowing when the sounds are all loaded. Another big request, because Soundpool keeps track of all the state of different voices, you don't have a lot of visibility on what's going on. And if you're pausing your application, you don't know which streams to pause. So we added an API for automatically pausing all the streams that are currently playing. And then the next bit is auto-resuming all the streams that are playing. So Soundpool is a little more friendly in that respect when you don't have to keep track of all the streams that are playing. I talked about audio routing improvements. We have the stream voice call is now routed to earpiece by default. Previously, I think it went to speaker. So if you have an application where you want to output to the earpiece, a good example is a voicemail application. Users have an expectation of privacy in that case. You don't want your voicemail necessarily blasting. If your girlfriend is calling with some maybe not safe for work message, you don't want that to go out the speaker. So in this case, you can have it routed to the earpiece by default. And then you can call set speaker on to route it to the speaker if they want to. So a voicemail app, you probably have a speaker button to route it to the speaker. Another big request we've had is routing audio to the Bluetooth SCHO device. So SCHO is the 8 kilohertz synchronous link that is used for in-call audio. It's a low quality audio stream, but it's ubiquitous. Every Bluetooth headset supports it. A2DP is the high quality stereo streams, and there are a lot of devices that don't support that. So there was a request to be able to support Bluetooth SCHO output, so now you can do that. You call start Bluetooth SCHO, open your voice stream voice call, and it will get it routed out to the SCHO output. Again, useful for voicemail applications or other cases where you're just going to send out low quality audio. Again, privacy issues. Camera improvements. We have a new preview API if you want to do signal processing on preview frames. It allows you to, go back. Allows you to avoid GCs. The old way, we would allocate a buffer, copy the data into it, and then you would end up with a GC every time you stop using those. And this one, you can pre-allocate your buffers. You send them down, you in-queue them to the native code, and it fills the buffer and returns it to you, and there's no GC. So we actually found that it doubled the frame rate for Goggle's application, for example. And let's see, there's also an API for compressing YUV frames from the preview to JPEG. So if you're trying to do like a webcam type application, you can take the preview frames, encode them as JPEG, and then ship them off over the Wi-Fi. And we're actually getting, on Nexus 1, I think about 10 frames per second over a Wi-Fi connection. So it's pretty decent. There's a no thumbnail mode for the JPEG encoder. Previously, we automatically generated a thumbnail. If you're doing really small JPEGs, that doesn't make any sense. So there's a way to tell it. You don't want the thumbnail generated and reduce the size of the JPEG. Camera also reports field of view and focal length parameters in EXIF. So now you can get that data back for AR applications and things like that. It can be pretty useful, determining what the field is you're looking at and using it for signal processing. And then we added exposure control settings, so you can, go +1, +2, -1, -2 on your exposures. And then finally, we added portrait mode support. We kind of had a hack in for some devices previously that I know a few developers out there figured out. It was never intended to be supported. We now have an official way of supporting it. I'm going to skip this because we're trying to catch up. And I'm going to talk about roadmap really briefly, and then we'll go on to Q&A. So in the next release, we're planning to introduce an OpenSLES API. OpenSLES is a huge surface. We're going to start small and build up from there, but the intention is to expose a native audio API. And OpenSLES will be the abstraction layer for that. That means basically all the audio track stuff in native code will get converted to an SLES layer. We actually have bits of that code up and running now. We're going to add OpenAL support, OpenAL as a shim over the OpenSLES. So basically, for those of you who are writing applications that use AL on other platforms, it should make it a lot easier to port your games or other applications for that matter. We're adding, as part of the OpenSLES, we're going to add the effects processing stuff. So that allows you to put in equalizers or things like that. We're also going to start exposing some of the low-level media APIs. Specifically, what we're going to do is have a Java API that allows you to build the player graph dynamically in your application. In particular, if you have a streaming format that we don't support, maybe you've invented the best RTSP protocol in the world and you want to do some extension or something like that. One of the problems has been you couldn't get access to the codecs, and it was really hard to do that. So this will actually allow you to build the graph in your code, and then again using something similar to the techniques we talked about with audio track. If you want to do native processing where you do something to the frames or whatever, you'll be able to get access to it through native code. Yesterday we announced VP8. Open source to the world. We're saying now that we're going to, I think I found another mic down there. We're going to support it in the next Android release. Unfortunately, the bitstream specifics were a little too late for the Froyo release, but we have it up and running in our next release. And so it includes VP8 support, Vorbis support, and WebM, which is our Matroska specific support for VP8 and Vorbis. We're going to add a FLAC decoder. We are going to add AAC LC encoder, software encoder for the devices that don't have hardware support already. And we're going to add an AMR wideband encoder. And those will both be open sourced codecs, so all the code would be available. Obviously, there's still licensing issues. There are patents that you have to license if you have a device, but the code will be open. And now we're going to move on to Q&A. I'll bring up the slide again if you want to follow in Wave. So anybody want to come up to the microphone?
Hello?
Yeah.
Now, one question I had is when to release the media player, because in Android there's no concept of exiting an application. So if a user pauses playback, how do you know that they won't, is that the time to release the media? How do you know that they won't necessarily want to start playing a second later?
Oh, so I didn't quite understand the question. Could you try it again?
Yeah, so I don't quite understand when I should be calling, when I should be releasing, when I should call release on the media player. Because if you, because you don't necessarily know when the user is kind of done with your application. For example, if they just pause it. Right?
Okay. So yeah, right. So if they're just pausing it, I think you probably need to make some intelligent choice. Like maybe you send yourself a delayed message at 5 seconds, and if they haven't restarted it in 5 seconds, then you tear it down. And a good example, so let's say you wanted to resume playing where you were, you get the current play position and you save that off, recreate the media player and seek to that position and start playing again. But I wouldn't go too much longer than that because you leave that thing up, the DSP, even if it's not doing anything, is still consuming energy.
Thank you.
Does your Audio Focus API have any support for conflicts between recording and playback, or two different recording devices trying to record at the same time?
Two different recording. So the question was, is there a conflict between recording and playback?
Yeah, so that's part of it. Recording and playback, or two different recording apps.
Okay, so we don't have a concept of two different recording inputs yet. I think there's, if I'm not mistaken, there's a source in the audio track or audio record interface, so you could potentially have more than one. There's no reason I could think of that we couldn't support multiple inputs at the same time. Conceptually underneath, it would just mean there's a record thread in the media server that would need to be duplicated for multiple inputs, but there's no reason from a platform perspective we couldn't do that. And as far as recording and playback at the same time, that should work. The issue you have with recording, if you're playing something on the device, you probably have some leakage from the speaker back to the microphone, for example. And we don't have any way to use the acoustic echo cancellation algorithms that are typically built into the baseband. So you have to do that yourself.
Yeah, I was more interested in preventing it than allowing it.
Oh, okay. Yeah, there's no way to prevent it.
Hi, we have a media streaming application that we're working on that has content behind authenticated, protection SSO, and we had a little bit of difficulty because the media player allows you to supply a progressive playback URL, but there's no way to manipulate the cookie collection or anything with that. Are there any changes in that area?
I know there's a feature request in. I'm not sure. Hopefully we'll get to that in the next release, but it's definitely not in Froyo.
Okay, thanks.
That's a good one, and it's definitely something we wanted to deal with. By the way, just some people have dealt with that by having a proxy server on the device that does that.
Dave, do you have any plans for bookmarking? Right now, applications don't know when a particular part of the audio stream has actually reached the codec. So if you're giving directions, for example, you don't know where you are in that stream.
So basically, you want to know what the latency is through the playback path?
Correct. And if it gets paused, that you can actually find out that it was paused and it hasn't reached it yet.
Right. So there's no provisions for that yet. I think we get that through the OpenSLES interface. If I'm not mistaken, that drives the latency all the way back. So we should be able to get that information when we get to there. AudioTrack doesn't do that now, and there are some challenges to that. If you look at like Bluetooth, for example, we have no idea how much audio is actually getting buffered in the Bluetooth device. It can be hundreds of milliseconds. So it's somewhat nebulous what that actually means. On device, we should be able to get a better number.
Hey, I have two questions. Do we support track level volume control? I know that in Android we have different streams and each streams have volume. Can I have two applications playing same music streams, but can I have two different volumes for 2 different tracks. Is that supported today?
Well, yeah, so each audio track has a volume control, and the media player is built on top of audio track, so it has a separate volume control, and there is a, if I'm not mistaken, there's a set volume interface on the media player. So you can actually set the individual volume for each media player, as well as each audio track.
Okay. The next question is, can I route? Today I know routing is something is taken care of by the framework. Is there any plan of giving control to the application to say that, hey, track 1 routed to headset, track 2 routed to speaker? Is that some kind of, or to Bluetooth?
So yeah, the question is, can you change routing for specific tracks? A lot of the devices that we deal with don't actually allow for that. We're seeing new devices that have sophisticated mixers down, typically in the baseband or a DSP or something like that, that have these fancy routing matrices, sorry. And you know, we should be able to expose that at some point. Right now, most of the devices, like if you look at the G1 and the MyTouch, there's only one output, and we can route it to SCHO, we can route it to A2DP, we can route it to the speaker, but we can't do a separate route. There is a concept in Froyo of what we call a direct output, and we're using that for some things like voice dialer now works over SCHO. So we can take that one output and route it, but there is no mixer for that. And it may not necessarily be supported on all devices. Okay. So there's a lot of issues we have to work with on the chipset and hardware manufacturers.
Yeah, last question, any support for FM radio? Because we saw some devices being added in
FM radio?
Yeah.
Yeah, I mean, we're still working out the details on that. We've had a couple of proposals, none that I was particularly excited about, but I think we'll probably come up with something. One of the things, a lot of stuff we do is device-driven, it's product-driven, and since if we're working on something, we kind of think about what we want in that until we actually have one that has an FM radio we're exposing as a feature. We don't have it's not highly prioritized, so okay. Hopefully maybe the next year.
Yes, messing around with the ringtone picker,
yeah.
I noticed that there was a parameter there for DRM available. I was wondering, is this open to developers to use, and how to use this?
The ringtone picker, what was the
I noticed that there was DRM support. I was wondering how we would access this.
Oh, yeah. My advice is stay away from the DRM stuff. We had this forward lock stuff that we did for our first device. It's not really well integrated into the system. So I didn't get into all the roadmap stuff, but we are working on a DRM integration for the next release. And it should be easier to do what you want to do, I think, at that point. Okay. But the stuff that's there now is not well supported.
All right. Thanks.
Unfortunately, sorry about that.
There have been discussions on Google Groups that you'll be bringing in stage fright and replacing that with packet video OpenCore. So yeah. Can you tell us, is that true, and what is the highlights of stage fright? Okay,
so the question is stage fright versus OpenCore, probably versus GStreamer versus who knows, whatever media framework might be out there. So we started stage fright as really the vehicle for supporting Flash. It was intended to be a lightweight framework that allowed us to do essentially what I was talking about earlier, expose the stack so that you could send elementary streams down to the codecs, and the framework would handle all of the AV sync and all that stuff. So as we got further into that, we said, if we'll add a stream extractor, we'll add this and that. The next thing you know, we had a media framework. It was we kind of accidentally fell into it. We've been talking to Packet Video, and they're going to be cooperating with us on stage fright. So in the long run, we're going to move away from OpenCore. We hope to do that in the next release. For Froyo, it's kind of a mixed bag. We have stage fright for local file playback and for HTTP progressive. OpenCore is still providing the authoring side and RTSP stack. So the next piece is to move those over and then expose some of these new APIs. For a hardware integrator, there's a little bit of extra support because you basically have to take your OpenMax codecs and put them into both frameworks, but we think that's not too painful. And that'll be one release, and the next release, it'll all be in stage fright. That said, if somebody decided they wanted to go with OpenCore, or they want to go with GStream, or they want to go with whatever, we're supportive of that. The requirement is that you pass the CTS tests, and CTS will include whatever new APIs we invent on top of stage fright. And I think that's going to kind of force people to head to stage fright, although I wouldn't preclude somebody taking GStreamer and making it work. Did that answer your question?
So could you just say the differences again between the use cases when OpenCore is going to be used in Froyo and when stage fright is going to be called?
So OpenCore will be used for RTSP and authoring. So the media recorder is stage fright. If you have an RTSP URL, that's that's OpenCore. For RTSP, also OpenCore. Everything else is stage fright.
So somebody who's integrating a new codec will have to have a version integrated with OpenCore as well as stage fright.
If you're using OpenMax, it's really just a matter of dropping it into the tables for the two frameworks.
And do you have any documentation available as to about stage fright?
Forthcoming. When we put the source code out, we'll have that information as well. I can take one more question.
I was wondering if you could comment on how Android right now or in the future is going to handle with multiple audio streams or channels like surround sound, what with Google TV and devices with mini HDMI out, things like that. So
OpenSLES has a lot of the answers to that. There's already provisions in that. We're still thinking about how the surround stuff works. Google TV, I think, is farther ahead. Even though they're both based on Android, the actual trees are separate at this point. We're going to merge them later. So they're probably better equipped to answer that question right now. But we'll have, I would imagine by the end of next year, we'll probably have some kind of solution for that.
All right, thanks.
All right, thanks everybody.